there are two inputs to the multiplexer. One is the scan input, so I will call this as parallel input, and I will call this as the serial input. Okay, so this is my parallel in. PIN or parin, okay, and this is my serial. And this guy is my control signal. I will call this as scan enable. Okay. So, right now scan enable is 0, so it is going to take parallel in. If I change this, it will take serial in. The other things are very similar. We have to enable your, this enable is permanently connected, and this preset is permanently grounded. And this is my asynchronous input, this is the reset. Right, and then I have an output. Okay. So, if the reset is high, the output goes to 0. If if the reset is low, oh, I forgot the clock. Okay. If the reset is low and the clock is initially low, and let us say serial input is high and the scan enable is high, if I toggle the clock, you will see that this 1 gets shifted here. Okay. And in the next clock cycle, maybe I will make serial in low, right, and this time you will see that a 0 got shifted. Okay. So, whatever is in the serial thing will get shifted. Similarly, if I make scan enable 0 and parallel in equal to 1, and if I clock the signal, you can see that the parallel input got loaded. Okay. So, this is a simple scan flop. Now, I can take a number of these scan flops and create a scan reg. So, we will create a 3-bit scan register. So, I have 3, I think I forgot to label the output. So, we can call it Q out or next state or whatever you want to call it. Okay. So, in my example, I had an incrementer, and I will have to have 3 of these guys. And I will also include an incrementer. Now, the outputs of the incrementer let us say this is Y2, we will also need a scan enable and a scan in and a scan out. Okay. Now, the scan in, let us call it a scan in. Let us call this scan out. The scan in must go to the scan in, sorry. This is a scan enable, this can go here, okay. And the scan in should go to serial in. Okay. Oops, sorry, be careful on this, you should not end up putting some extra metal. Okay. Now, the parallel in must be the Y2. So, Y2 or scan in, one of them will be shifted in depending on the scan enable. If scan enable is 0, it will shift the Y2. If scan enable is 1, it will shift scan in. Similarly, Q out should go as parallel in. No, I am sorry, Q out should go as serial in. Y1 should go as parallel. And Q out should go as serial. Okay. Scan enable is the same thing. Oh, you know what, we forgot to name the clock, and so this has to be labeled clock. Okay, and this has to be labeled reset. Okay. So, you can see that now the clock and reset have also come in. So, we will bring in an input called clock and connect the clock there, and we will bring another input called reset and we will connect the reset over there. Okay. The clock has to be connected everywhere. And similarly, the reset has to be connected here. Okay. Similarly, this reset has to be connected over here, right, and this clock has to be connected over. Just, okay. And scan enable also should get connected everywhere. So, you can see that it introduces a lot of routing issues, right. I mean, imagine tens and thousands of these flip flops, and scan enable has to be routed everywhere, scan clock has to be routed everywhere. Q out goes to, oops, sorry, Q out goes to serial in, okay, and parallel in goes to this Y naught. Okay. And then Q out goes to serial out. Okay. And this the Q out of each of these must also be sent back to the x2, x1 and all that. So, we have to send this back here. Right, and this Q out of this guy has to go back. And last but not the least, okay. So, let us see how this works. Initially, let us say we reset the flip flop. So, all of them should be in the 0 state. Okay. So, we can maybe put a LED to see what is the state of these flip flops. So, when you reset, they are in the state 0 0 0, none of the LEDs are glowing. Okay. Now, let us just simulate the normal operation. That means scan enable is 0, it does not matter what scan in is, we have to simply keep applying clocks. So, we forgot to reset must be 0. Now, we keep applying a clock. Oh, there is some mistake in our this is 0, this is 0, this is 0, this is 0, 0 and 1. You know what, I think I made a mistake. No, that is okay, right, parallel. Why is it not loaded there? This parallel should have got loaded here, right? See, I think I have labeled the things wrongly. See, in the scan flip flop, I think this is a reset. Okay. So, there is an error. Whatever is clock has become reset and whatever is reset has become clock. If I change it, I am worried that it may go and disconnect everything. See, this should be reset. Okay. And this should be a clock. My worry is that it will disconnect everything now. No, luckily it has not done that. Okay. So, this is a reset. So, everything is now in 0 state. Now, I bring back the reset and then start applying the clock. See, when I said 0 to 1, it went to that state, then 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. So, I hope everybody is convinced that we did not change the functionality is the same, okay, it is still acting as a count. But for testing purpose, if my intention is to send this to, let us say, the 101 state, okay, then I do not want to cycle this through so many increments. So, what I will do is I will set the scan enable to 1, okay, and scan in is, let us say, 1, right, and I will clock it once. So, now that 1 came here. Next I am going to send it to 0 and again clock it. So, that 1 came here and the 0 came here, and again I can make it 1 and clock it once. So, that 101 came now. Okay. So, I have sent it to 101 state in 3 clock cycles. Okay. Even if this was a very big register, okay, even if it was a 32-bit register, if I have to send this to some arbitrary state, I can do it in 32 clock pulses. Whereas, if I had to depend on the functionality of that counter, then it may take exponentially large number of cycles, like 2 to the power 31 cycles or 2 to the power 32 cycles, something like that. See, for example, if this is a 32-bit register and this is I have to send it to 1 followed by all zeros, then it will take me 2 to the power 31 clock cycles to get to that stage. Whereas, if I use this method, I can, in 32 clock pulses, I can change it to that state. Okay. So, I have now applied 101, and if there is a fault here, it may get captured in the output. Okay. So, right now I may not be able to simulate the fault so well. See, for example, if I try to create a stuck at one fault here, let me see if that is possible. Let me inject a fault. Okay, how do I inject a fault? I can try to put a multiplexer here. So, what I am going to do is I am going to take this guy here. See, normally it used to come here. So, I am going to send this here. See, this is just for injecting a fault. And I am going to put a 1 here. And this control signal, if it is 1, oops, sorry. If this control signal is 1, then I have injected a fault. Okay, so this is a fault. So, this is inject fault. Okay. If it is 0, then there is no change in the operation. Okay. And this guy goes back here. Okay. So, right now it is inject fault is 0, so things should not change. So, I will start by resetting the flop. Then I will change the clock to 0. I will change scan in to I will change scan enable to 0. I will make sure that no change is there, right. See, this is still the same flip flop. Okay. So, verify. Okay. So, 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. But if I put a fault here, okay, so it not work correctly as a counter, you can verify. So, when I did a clock, see, from 0 it went to 1 1 state, okay, that is a faulty state, then 1 1 0 state, then 1 1 1 state. So, it is not behaving correctly. So, in the presence of fault, okay, let us try to see whether we can catch that fault by shifting in a test vector. Okay. So, I will shift in a vector which has a 0 in this. So, let me see if I can shift in 0 0 1. Okay. I will make scan enable high, reset is low, and I will keep clocking. Okay. So, you can see that I should have put 0, right. So, I was able to send it to the all 0 state. Okay. Let me do 1 0 1 state, 1 0 1. So, I have put in a 1 0 1 state. Okay. So, when this guy increments 1 0 1, it should go to the no, that is not a good 1 0 1 is not a good test vector, because it will send it to 1 1 0, the faulty circuit will also have 1 1 0. So, we should send it to maybe this is a good test. So, I have sent it to 1 1 0 state. No, this is also not a good state. See, now it is in the 0 1 1 state. So, when the counter adds, it should produce 1 0 0, but in the presence of fault it will produce 1 1 0. Okay. So, let us try that. So, I will put scan enable to 0, and then I will capture. Okay. See, it produced 1 1 0. Okay. So, it is in the wrong state now. I expected 1 0 0, but it has produced 1 1 0, right. Now, I will shift out. Okay. I will shift out the contents by changing scan enable to 0. So, I am waiting for the second bit, it should be 0 according to me, right. But now I get a 1 because there is an error. Okay. So, I can shift it out. So, I thought okay. So, that will tell me that there is a fault. Okay. So, what is the new thing that you learned today? I told you how to inject a fault. Okay. How did I inject a fault? I put a multiplexer here. In the normal mode, that is when fault inject is 0, then the output y2 is what comes here. But in the faulty mode, a stuck at one fault has been injected. Okay. So, if I keep it as 1, the fault gets injected here. So, let me try one more example. See, if I scan in all zeros, for example. Okay. So, let me scan, I will keep scan in equal to 0, scan enable is 1, and let me scan in as 0. So, all are 0 now. Okay. Now, a good incrementer which has no fault will produce a 0 0 1, but because of the stuck at 1 fault I will get a 0 1 1. Okay. So, let us now try to capture this. So, how do you capture? I should send scan enable to 0 and I should clock it. See, I got 0 1 1. Okay. It produces a wrong output. Then I can sort of enable this scan again and I will see what comes out. Okay. I can do that by clocking. So, I got 1 1 0, okay, when I shift it out, and that can be sort of compared with what was being expected. Okay. I was expecting 0 0 1, but I got a 0 1 1. So, then I conclude that there is some problem in the circuit. Okay. There is a fault. Okay. Is that clear to everybody? I hope. Okay. So, let me explain this one more time.